Hi everyone, welcome to Incognito Engineer. In this video, I am going to explain the history of big data in a very simple way. We will go from the early days of single machines all the way to modern cloud and AI systems. Let's get started. In the early days, the solution to growing data was simple. Just make one computer bigger. Add more CPU, add more RAM, use faster disk. This is called vertical scaling. But data kept growing faster than hardware. Eventually, even the biggest machine couldn't keep up. This is when the need for a new approach became clear. Think of your computer's CPU as an example. In the early days, processor had only one core, like the old Intel Pentium chips. That single core had to do all the work. Engineers kept trying to make that one core faster, higher clock speeds, more power, but they ran into problems like heat and energy limit. So the industry changed the approach. Instead of making one core extremely powerful, they decided to create multiple cores working together inside the same processor. And that's when we started to see dual-core CPUs, then quad-core, then octa-core, and now even laptops can have more than 16 cores. They stopped scaling up and started scaling out, and the exact same thing happened in data engineering. For all this, engineers started choosing multiple machines working together. This idea is called horizontal scaling. Instead of making one machine bigger, we simply add more machines as we need them. This was the start of distributed computing, which is the foundation of modern data systems. Once we had many machines, we could also split big jobs into many smaller tasks. These tasks run at the same time across different machines. This approach made data processing much faster and more efficient. This was a major step toward what we now call big data architecture. In 2004, Google published the MapReduce paper. This explained how they processed massive amounts of data using thousands of machines. This paper became one of the most important ideas in big data. It changed how the entire industry thought about large-scale data processing. MapReduce works in two simple steps. First is the map phase. This splits the work into smaller pieces and distributes them across many machines. Each machine processes its own piece of data independently. Then comes the reduce phase. This takes all the results from the map phase and combine them to produce the final output. So it's a simple idea, but with a huge impact. A year later, in 2005, Yahoo created Hadoop. It was an open-source version of Google's MapReduce system. Hadoop included HDFS, which is Hadoop Distributed File System for storage, and MapReduce for processing. Companies like Facebook, LinkedIn, and Twitter quickly adopted it. This created the first big data ecosystem. HDFS solved the problem of storing massive amounts of data. It splits files into 128 megabyte blocks and stores 3 copies for safety, or we can call it redundancy. It runs on normal, inexpensive machines, making it very cost-effective. This made it easy to store petabytes of data. Because Hadoop was open source, anyone could use it. Startups gained access to powerful tools, large companies adopted it across their systems, and big data became available to almost everyone. As Hadoop grew, more tools were added. Hive lets users write SQL and big data. Pig helped with scripting and transformations. HBase provided a NoSQL database. Scoop moved data between systems. And Yarn helped manage cluster resources. This turned Hadoop into a complete platform. But Hadoop wasn't perfect. The NameNode, which stores all the metadata, was a single point of failure. If it went down, the whole cluster went down. this was a major reliability issue. HDFS version 2 fixed this problem. It introduces an active name node and a standby name node. If the active one failed, the standby one took over automatically. This made Hadoop much more reliable and stable. Even though Hadoop became more reliable with HDFS 2, there was still a big problem. Hadoop MapReduce was slow. Why? Because after every map step, the output was written to the hard drive, and before every reduce step, that data had to be read back from the hard drive again. This happened for every stage of processing. So a lot of time was spent writing and reading data from disk, which made the whole process very slow, especially for jobs that needed multiple steps or iteration. To solve this issue, a new system was created, Apache Spark. Apache Spark was designed to solve this big problem in MapReduce. The biggest difference is that Spark uses in-memory processing. Instead of writing intermediate results to hard drive, Spark kept the data in RAM as much as possible. This makes Spark 10 to 100 times faster for many workloads, especially ones that repeat operations on the same data. Spark became the new engine for fast big data processing. Spark is not just fast, it's also very flexible. Spark comes with built-in libraries like Spark SQL for structured queries, Spark Streaming for real-time data, MLlib for machine learning, GraphX for graph processing. All of these use the same Spark engine and the same API, so developers can handle many types of workloads using one unified system. Because Spark is so fast, it changed how companies think about data. Old systems processed data in hours or days. Spark reduced this to minutes or seconds. Today, many systems can process data in real time, providing insight for dashboard monitoring and machine learning in an instant time. Spark played a major role in moving the industry from slow, batch jobs to near real-time analytics. Around 2008 to 2010, the industry ran into another challenge. Traditional SQL databases were great for structured tables, but they couldn't handle the huge amount of unstructured data coming from mobile apps, social media, and web traffic. This led to the rise of NoSQL databases like MongoDB, Cassandra, and DynamoDB. These systems were designed to scale horizontally, store flexible data formats, and handle very high write speeds. They became a key part of modern big data architectures. As companies collected more and more data, they needed a place to store everything, even if that data wasn't structured yet. This idea became the data lake. A data lake stores raw, unprocessed data cheaply and at massive scale. It doesn't require a fixed schema, and it separates storage from compute. Systems like Hadoop HDFS, Amazon S3, and Azure Blob Storage made it easy for companies to build large data lakes for analytics and machine learning. Next came cloud data warehouses, which made analytics much faster and easier. BigQuery arrived in 2011, Redshift in 2012, and Snowflake in 2014. These systems separated storage and compute, scaled automatically, and allowed companies to run fast SQL queries on huge datasets. Because they were fully managed and cloud-based, companies no longer had to worry about infrastructure. They could focus on analyzing data. Before cloud computing, companies had to buy and maintain their own servers. This meant expensive hardware, long setup times, and a fixed capacity that was hard to upgrade. Cloud platforms completely changed this model. Now you can create clusters instantly, scale them up or down, and you don't need to buy any physical machines. This made big data processing much easier, cheaper, and more flexible for everyone. Cloud platforms give us something that wasn't possible with traditional hardware, almost unlimited scale. You can store as much data as you want, from gigabytes to petabytes or even exabytes. and you can use thousands of machines on demand whenever you need them. You also pay only for what you use, which makes it much cheaper than buying your own servers. This made big data accessible to far more companies, and it helped the industry grow even faster. Today, we are entering the next phase of big data, the AI native era. We now have data lakehouses, which combine data lakes and warehouses into one system. Real-time machine learning pipelines are becoming common. Vector databases are used for AI search and embeddings, and even ETL and data quality tasks are starting to be automated with AI tools. The future of data engineering is faster, smarter, and much more automated. And that brings us to the present. Big data has come a long way, from single machines to Hadoop to Spark to cloud, and now into the AI era. Thank you for watching. I hope this simple explanation of the history of big data helped you understand how the field evolved over time. This is my second video, so if you found it helpful, please consider subscribing to Incognito Engineer. More beginner-friendly data engineering videos are on the way.